Okay, so let's talk a little bit about the alkylation of the alpha carbon using this enolate chemistry. So, it's the same idea that we've been talking throughout chapter 21, and that is that the alpha position is acidic, and so alpha carbons can have their protons deprotonated with a strong base. Now, in order to do alkylation, we really need the enolate to be completely transformed from the keto form. So we're going to use one of those really strong bases, such as lithium diisopropylamide, so that it's really going to completely remove the proton and turn it into that really strong nucleophile. And that's really the key, is the enolate structures we've been seeing throughout this chapter. They're really strong nucleophiles. So we can really take the idea all the way back to what back in chapter 7, where we learned that you can take an alkyl halide and have a nucleophile attack it as the halogen falls off, and now the nucleophile is attached to whatever that alkyl chain is. So that's the same thing we can do here to do an alkylation at the alpha position. We can make the alpha carbon become an enolate, which is a strong nucleophile, and then have it attack an alkyl halide via an SN2 mechanism. And now this R group that was connected to a halogen is now connected to the alpha carbon. But the same ideas that we learned back in chapter 7 in OChem 1 still apply here. And that is, when you're dealing with a strong base, strong nucleophile, you really have to worry about competition with the E2 mechanism that essentially involves the same reactants, alkyl halides and strong bases. And so whenever you're dealing with a secondary or tertiary alkyl halide, you're really going to end up with the majority of E2 elimination product and not substitution product. So we really have to limit ourselves to only doing alkyl chains or attaching alkyl chains at the alpha carbon that come from primary alkyl halides. And once again, as I said earlier, we also have to worry about a competition with the aldol reaction that we've learned about. And so that happens whenever you use a base that partially deprotonates the alpha carbon, that is on only some of the molecules of that ketone, aldehyde, etc., and leaves the other parts of them still in that keto form, and that allows them to attack each other, and you can get this kind of dimerization. We want to avoid that, so we're going to use a super strong base that doesn't allow the keto form, the carbonyl carbon to remain that and instead transform into the enolate 100%. So we're going to use things like LDA or NaH. There is a regioselectivity issue that we also have to consider if we're dealing with unsymmetrical ketones, and that is two different enolates can form. So when we look at the enolates, we could either form, when you have an unsymmetric ketone, you can either form the more substituted enolate. We're doing the resonance form of the enolate where the negative charge is on the oxygen, we're looking at that form to compare. And so you've got the more substituted enolate and then the least substituted enolate. Now, what that leads to is there are two different product outcomes you could have. Are you going to alkylate at the at the alpha carbon that's least substituted or the alpha carbon that's more substituted? It turns out we can control that, so it actually becomes synthetically useful. The way we control it is that whole thermodynamic versus kinetics issue. It turns out that the alkylation, or I should say the formation of the least substituted enolate, is more favorable in a kinetic situation, and the formation of the more substituted enolate is favorable under thermodynamic conditions. And what that's going to represent is it's easy to make the least substituted enolate, but it's harder to make the more substituted enolate, but it's also more stable. And so it's the same idea. We're going to use temperature like we did back in the conjugated diene electrophilic addition. We want to use temperature to favor the thermodynamic versus the kinetic. And so thermodynamic, as we're going to see, favors lower temperatures. Excuse me. The kinetic product favors lower temperatures. We also, if you notice, are going to focus on using LDA for that case too, because it's a much bulkier base and it'll favor deprotonating the less substituted carbon over deprotonating the more substituted carbon. That way, when we then add our alkyl halide, it will end up on the least substituted carbon. That'll be the major product under these conditions: colder temperature, bulkier base. If we want the more substituted carbon to end up to be alkylated, then we need to have conditions that favor the thermodynamic product. One of which being temperature, we want it to be warmer. Now, it doesn't have to be heated like to boiling or something, because the cold temperature to get the kinetic is -78. So we just need like 25 or room temperature. You may also notice that we're using sodium hydride, which is a strong base, much like LDA, but more but less bulky. It's smaller, and so that size issues, those steric issues, are also going to favor, or at least allow it to more easily access the more sterically hindered, more substituted alpha carbon. So in the end, your choice of conditions will control where that alkylation occurs on your ketone starting material. So now I wanted to kind of jump ahead to something that's involved in the next reaction we're going to look at, and that is decarboxylation. It's going to be a multi-stage reaction. This is one of the last steps, but I wanted to focus in on it first because it's very interesting. What we find is whenever we have a carboxylic acid functional group that's 3 away, or 2 away, I guess, from another carbonyl site, it's able to undergo a transformation when you merely heat it. So this R group can be anything. It can be a hydrogen, it can be another OH group even, it can be a carbon chain group. And then this decarboxylation can occur whenever you heat a molecule like this. The way that this reaction occurs is if you think about this molecule and rotate this bond around, you'll find that the hydrogen can actually be located in an arrangement that looks very similar to a 6-atom ring, which, as we learned way back in OChem 1, is a very favorable structure. To have 6 atoms around in a ring, it makes any processes or just overall general energetics of that structure to be more stable, and thus it makes any transition state involving that arrangement more stable. And so what we find is this configuration allows a proton to transfer from the OH on the carboxylic acid to the oxygen of the neighboring carbonyl oxygen. And then it's essentially a paracyclic process. So as that proton transfers, the electrons holding onto that proton come down to form a double bond between the carbon and the oxygen. And the bond that's connecting this alpha carbon to this carboxylic acid carbon, it releases that carbon and comes over, filling in these electrons that just moved over to attach to the hydrogen and forming a double bond. That what essentially does is it breaks the molecule into 2 pieces, producing an enol and a carbon dioxide molecule. That's why it's called decarboxylation. You're releasing the CO2, transforming, essentially removing this piece of the molecule, the carboxylic acid, generating an enol. And then that enol can or will then tautomerize back into the ketone structure. So essentially, the net transformation is you've removed that carboxylic acid group, the carbon and the 2 oxygens, transforming it into just the keto piece or the ketone piece. So now let's look at malonic ester synthesis. Now, it's a little bit of a misnomer. Malonic ester synthesis isn't about synthesizing malonic ester, but it's about using malonic ester in a synthesis. What the net transformation is you're going to take an alkyl halide and essentially convert it into a carboxylic acid where there's 2 additional carbons compared to whatever that R group or that chain of carbons was that was connected to the halogen. Now, the way we do this is we're going to start with diethyl malonate or malonic ester. And so it has this structure right here. It's essentially 2 ethyl esters that are connected together by a shared alpha carbon. And just like we've seen in the past, these 2 carbonyl sites that have a single carbon between them, that alpha carbon has extra acidity to it. It's got a pK somewhere in the 9-ish region. And the reason for that is because there's extra resonance that stabilizes its conjugate base. So it's quite easy to transform it fully into the enolate form with a milder, relatively speaking, strong base such as ethoxide. Now, You do have to be careful in malonic ester synthesis as well as its cousin acetoacidic ester synthesis, because both of those involve an ester, and we don't want to mess oftentimes with the ester group, or at least we tend to want to be careful on that. And so we're going to generally match our base with our ester. And so in this case, notice how all these esters are ethyl esters. They have ETOs attached to them. We're going to use ethoxide then as the base, not methoxide, even though it would have the same basic property as ethoxide. We don't want it mixing up or scrambling what this is at this site. So what happens after you remove that alpha proton, what you generate is the enolate, which is a strong nucleophile. So what you do is you then add an alkyl halide to then undergo an SN2 mechanism or reaction, a substitution. So the enolate is going to attack the R group as the halide falls off. Once again, same thing, SN2 mechanism. We generally want to focus on primary alkyl halides. Secondary and tertiary will generally undergo elimination instead, as we mentioned earlier. Now, the next stage is adding acidified water, or H3O plus in water, hydronium in water. And what that's going to do is it's going to take the two ester groups and it's going to transform them into carboxylic acid. Some might argue that's why it kind of maybe doesn't matter whether we have sodium ethoxide or sodium methoxide, and end up scrambling these into MEO groups if we were to use methoxide, because we're going to get rid of them anyways with this hydrolysis. But I generally still argue that you should use whatever the ester is back in the first step here, you should use its matching alkoxide as the strong base. But we are eventually in this third stage here going to transform the esters via hydrolysis, acid catalyzed, into their carboxylic acid forms. The last stage is when you have, and we mentioned it in the previous section of this play pause video, when you have these dicarbonyl groups that are 1,3 from each other, 1, 2, 3, 1,3 dicarbonyl groups, where one of them is a carboxylic acid, you're able to cause this molecule to undergo that decarboxylation that we discussed previously, where a CO2 molecule is going to fall off, leaving you, in this case, it was this one, fell off via decarboxylation, leaving you with just one of the carboxylic acids, the alpha carbon, and the R group that was attached. So the overall process is first you add a strong, usually alkoxide base with its matching alcohol as the solvent to transform this diester into its enolate form within that central alpha carbon. You then add some kind of alkyl halide that will undergo SN2 substitution, so typically a primary halide. Finally, you add H3O plus and heat it for a while, causing the esters to transform into carboxylic acid, and then the carboxylic acid to undergo decarboxylation. There is a slight variation method in which you can actually dialkylate it, and you can selectively dialkylate it. In other words, not always use the same R group. You can attach two different R groups because you're going to introduce, instead of these two steps alone, you can introduce a second set of those types of steps. That is the addition of a sodium alkoxide followed by another different alkyl halide, and add two R groups to the alpha carbon before adding the hydronium H3O plus and water and heating it, removing one of those carboxylic acids that you form with the hydrolysis via decarboxylation. So what I want you to end this play pause video with is see if you can figure out what the product would be when you do this dialkylation malonic ester synthesis. Well, I'll see you in class on Tuesday, where we'll discuss acetoacidic ester synthesis and get into Michael's addition. See you then.